I'm going to talk about some work that we are currently doing on modeling and simulating lattice structures using inelastic beam models. And this work is done in collaboration with my PhD student Iman, who talked just a few minutes ago, and then Yash, Mistry, and Dhruv, Bhate from the Arizona State University. So the structure of this talk looks like this. First, I will present a brief motivation and introduce some of the previous works that we have done in this domain. Then I'll introduce the 3D beam model formulation that we use, and finally show its application to additive manufactured beam lattices. Before I will, after that, I will of course conclude with a summary and outlook. So in general, additive manufacturing enables the fabrication of quite flexible lattice structures and other kinds of metamaterials that very often or typically constitute of slender members, means that they are composed either of beam or shell-like microstructures. Depending on the materials used, they can deform elastically or inelastically and exhibit large deformations. When they do exhibit large deformations, then very often buckling occurs, which can either be seen as an issue or can also be seen as something that can be exploited in terms of designing structures with a specific behavior, for which, of course, for instance, auxetic metamaterials and chiral metamaterials are two good examples of where microstructures are used in order to get a effective behavior from a metamaterial that is typically not found in traditional materials. Furthermore, metamaterials can also exploit multi-physical and active behaviors like 4D printing methods that introduce shape changes based on temperature change or humidity changes or other kind of chemical or electric stimuli. And of course, one big advantage of using additive manufacturing to fabricate metamaterials is that we can design the microstructures that are to be fabricated very freely in terms of their topology, their shape, their geometry, and the materials that are used. Now, in order to exploit all this design freedom, we need to be able to simulate these structures efficiently and rapidly, so that we can also apply design optimization methods. And here we want to do this in the context of nonlinear 3D beam structures, basically because, like you've already seen in many of the talks today, that's a typical kind of metamaterial. So some work that we have already done when I was still at the Singapore University of Technology and Design is that we developed a 3D beam model and incorporated that into a design workflow that uses intra-lattice in Rhino, where basically we can now model and simulate three-dimensional lattice structures and predict their mechanical behavior fairly accurately, also in a large deformation regime. Based on this work, we then also developed some homogenization techniques so that we can homogenize the effective behavior of the unit cells of different kinds of microstructures, taking into account also effects like the buckling behavior, which is not trivial to include in the microstructure simulations. Furthermore, we developed some methods for doing design optimization in the context of 3D printing of beam structures. So at the top, you see one paper where we basically developed a design optimization workflow for shape memory effect-based 4D printing, where we considered large deformations and considered the temperature changes and material property changes due to the shape memory effect, but not really the thermodynamics of the shape memory effect. And at the bottom, you see a direct 4D printing approach, which was also mentioned by Kevin earlier, where basically we printed using PolyJet two different materials in the cross-section of a beam, and then due to some eigenstrains that are incorporated due to the printing process when there is a temperature change, these structures change their shape and evolve into three-dimensional shapes from originally flat ones. And also here we're able basically to simulate this temperature-induced or eigenstrain-induced deformation using the beam models. So how these beam models look like, these so-called geometrically exact shear deformable 3D beam models, is that we want to model the deformation of a three-dimensional beam, which can be initially curved. And the beam is described essentially in terms of the center line, which is a curve in the three-dimensional space, and the cross-section orientation, which is a rotation field in the three-dimensional space. So that means that the D1 and the D2, which are the first two columns of this rotation matrix field, they point in the directions of the cross-section, and the D3 that points in the direction orthogonal to the cross-section. And D3 does not have to be aligned with the tangent of the curve with R prime, which means that there can be shear deformation. So speaking about shear deformation, basically this leads us directly to the strain measures in this beam theory, which are a vector epsilon of translational strain, which captures basically the extensional or compressive strain and the two shear strains, and then a vector kappa for the rotational strains, which basically captures the two bending strains and also torsion strain. Now, typically in these 3D beam theories, a linear elastic constitutive model is used where basically the strain measures are mapped onto stress resultant measures. One could say the internal forces and the internal moments of the beam. And if the cross-section is homogeneous, basically there's no coupling between extension and bending, and we only have these terms A and C over here. If they are non-homogeneous cross-section, like the laminate cross-section that you see in the picture there, then we also have these coupling terms B. And if we want to model eigenstrains, then for instance, we can use these terms that are here in red. Now with these stress measures, basically we can formulate the balance equations of linear momentum and balance equations of angular momentum. And these are the two equations that need to be solved in order to determine these unknown centerline field and cross-section orientation field when the beam is subject to some external load. So already many years ago, we developed a novel approach in order to solve these equations, a so-called isogeometric collocation method, which you can find more details about in this paper. But basically, that's also important for what I'm presenting today, how the method works. But basically, what we can do with this method is that we can simulate model these three-dimensional beams. We can include functionally graded, laminate, and spatially varying cross sections. We can include also contact and dynamics in the simulation, and we can do all kinds of optimization, which you already saw in the 4D printing applications before. For instance, we can do optimization where we optimize the height ratio for such a laminate in order to get a desired 4D deformation, or we can optimize the behavior of a microstructure in its effective homogenized behavior, or also of a macroscopic lattice structure. But here we always use these elastic constitutive models, so we can only model elastic material behavior, meaning basically there is no dissipation, no viscoelasticity, no plasticity involved. So what we wanted to do next is basically to extend these models towards inelastic behavior, and we try to capture basically viscoelasticity, plasticity, and also the Mullins effect. So how we do that is basically by extending the one-dimensional theory of inelasticity to 3D beam models, and this has already been done also by other authors before. So essentially, you can imagine the whole material model using this mass spring damper analogy, like for instance a generalized Maxwell model where you have some springs and some dashpots which are in series, and then basically in parallel you have different elements, where here this would be the plastic element. And now for each of these branches or in total, you have a strain energy, which is the psi over here, or total internal energy function. And this depends on the strain measures, which are the epsilon and the kappa in the context of the beam. And then quite a bunch of internal variables over here, which supposed to capture the different kinds of inelastic effects that we want to model. So for instance, in the elasto-plastic branch over here, we have the elastic strain energy, which now depends on only the elastic strain, which is the difference between the total strain and the plastic strain for the axial strain measures and for the curvature strain measures. In the viscoelastic branches, so here I've just put one viscoelastic branch, but in the picture there could be more. We have as the energy over the spring, the difference between the total strain and the strain that would be on the damper over here. And then there's also for the Mullins effect a damage energy, and for plasticity also a hardening energy, which can include then also kinematic and isotropic hardening effects. So these energy potentials, typically they are assumed if you think of linear elasticity or linear visco-elastoplasticity in terms of quadratic potentials. So here I just write this one-dimensionally. The potential would depend on the strain in a quadratic fashion, where E would be the Young's modulus here. So basically you get the stress as the derivative of the strain energy function with respect to the strain, which means here you would have that sigma is equal to E epsilon, which is equivalent to the linear constitutive models that you saw 2 slides ago in the beam model. But we could also use here other kinds of nonlinear models. So for instance, we could use a Henke type strain energy or some exponential type strain energy, for which you see the curves over here. So basically the relationship between strain and stress is linear. For the quadratic strain energy in the Henke type, it would be the red curve. So you have some softening effect with larger strains. And in the exponential here, you would have an exponent of -4, even stronger softening effects. Now, in order to complete this inelastic material model, we also need evolution equations for all the internal variables, which are formulated in the typical way, basically how this is done also in 1D viscoelasticity and 1D plasticity, which means that for the plasticity, we also need a yield surface. And in the context of beam theory, it's not so clear how such a yield surface can be directly expressed in terms of the stress measures and the hardening variables that we define. So there have been some very nice recent works also by the group of Paul Steinmann in Erlangen, by Herrnberg, who discuss how this can be done in a meaningful way. And then we also need the damage model, for which the damage variable eta here is expressed basically in terms of only the elastic strains. It corresponds to a very established damage model by Ogden and Roxburgh. Yes, and basically we can do the plasticity here also in the rate independent fashion, like you see it over here, or also in the rate dependent fashion, where basically you have another damper in parallel to the plastic element over here. So of course, this was a very quick introduction into how this model looks like. We implemented this now in the context of our mixed isogeometric beam elements. You can find all the details about this implementation in this paper. And what we first did there was basically some validations where we compare analytical 1D models against the beam model when we just use it basically in uniaxial tension and compression, because basically then the response from the beam model and the 1D model should be identical. And likewise also in pure bending, the response from the beam model and the 1D model should be identical, which we showed over here for some cyclic viscoelastoplastic material behavior. And then we did some more studies on the model, which are shown over here, which all showed that it works quite well. So then we wanted to make the step and now apply this to additive manufactured lattice structures. So the first thing that we of course need to do is we need to identify the parameters of the material models that we want to use now in the beam theory. And therefore, we started with the collaboration with the guys from Arizona State University that I mentioned in the beginning, who fabricated some tensile samples using an SLS machine from PA12. And then they did uniaxial tension tests, which you see plotted in the dashed lines down here at different strain rates. And here we see basically that there is quite, initially the material behaves linearly elastic, say up to 2%. We can see a little bit of a difference in the curves that comes from the viscoelasticity, and then we can see that there is more or less a kink in the curve, which means there must be some plasticity. And now we model this using a rate-independent Elasto-visco-plastic 1D model, which has one viscoelastic branch, so only one branch over here, not more. And then you see basically the fit of this material model, 1D material model, to these uniaxial tension experiments, which corresponds more or less well. Now, basically, we use this model, this 1D material model, in our beam model, and we try to simulate a lattice structure in a compression test here, a BCC lattice, like you see it in the video over here. And basically, we model the beam structure using our isogeometric collocation method. In total here we have 260 beams and about 61,000 degrees of freedom, which is of course a lot less compared to when you would model the same beam structure using a three-dimensional finite element approach. And here you see a comparison basically of the experiments, which are always the gray curves here for two different diameters of the lattice structures, and the simulations that we do in the B model. And on the top, you also see some snapshots basically for this diameter 1.8 structure at different compressive displacements. And the structure here is 45 millimeters in size. So basically the 25 millimeter compression is like more than half of the structure already. And here you have a significant densification, a lot of contacts already. So overall, we see here a very good agreement, both qualitatively and quantitatively, of the experiments and the simulations. So basically, we can capture first the linear elastic behavior, then the instability, which also always then leads to plasticity. We see softening effects. We see very strong densification effects, which come from contacts. And we see that in the simulation and in the experiment at some point, it makes hardly any sense anymore to try to predict what's happening because it's just too random, basically. But what we can see from these plots is basically that we have this very good agreement, even for this highly nonlinear and highly inelastic behavior. And we also see that including all these viscoplastic inelastic effects is really crucial in order to get an accurate simulation of such a lattice structure. Then we did some experiments our own. We went to use our Prusa MSLA printer with the orange tough resin that is provided by Prusa. Here we did a more detailed characterization of the material behavior. So we did cyclic tension tests where basically we load and then we unload up to different strains and at different strain rates, which you see over here. And we did some relaxation experiments. And then we used a rate-dependent Elasto-visco-plastic model. We also fitted the damage parameters. And again, we get quite a reasonable agreement of the model and of the experiment. Maybe the unloading behavior is not so good, but yeah, still not bad in my opinion. Then we use this model now to simulate another lattice structure, which we fabricated from MSLA, where again, we have a BCC, for which we do a constrained compression test at two different strain rates. And here we see that we have a really good prediction of both the loading and the unloading behavior for this structure. Then actually, like, I think a month later or so, we printed a thinner lattice structure, which only has a diameter of 0.9 millimeters. And we did the experiments and we did the simulation, and there we realized that there was some deviation. So actually the initial results that we got, they were significantly stiffer than what you see in the plot over here. And then when we made some adjustments, so it could be that the light intensity that cures the material decreased, which means that the material might have become softer, or it could also be that there are some geometric tolerances, basically because the accuracy of the printer is 0.05 millimeters. So when we want a diameter of 0.9 millimeter, it could be a little more, it could be a little less. And then when we make those adjustments, we can still get a very good agreement of the behavior of such a lattice structure. But this means that we have to make some more detailed investigations of how these uncertainties, both in terms of the material parameters and the material behavior, and also the geometric uncertainties that come from the printing process, how they affect the lattice structures. And as a final validation, basically, we also printed an octahedron lattice structure, like you see it in the picture over here. We did a compression test on it up to different strains at different strain rates. And again, we get quite good predictions, quite good correspondence of the simulation and the experiment. So in summary, we developed a 3D beam model and an isogeometric discretization method that can capture elasto-visco-plastic material behavior and damage due to the Marlin's effect. This model is thermodynamically consistent because basically it is just a one-dimensional inelastic model that we generalize, and it can be characterized by relatively few and simple experiments because we just need basically uniaxial tension tests. And we showed the application for different materials in MSLA and in SLS to different kinds of beam lattices. As a conclusion, basically, we see that we got quite good agreements of the simulation and the predictions using these models. And it is really crucial that instabilities and all the kinds of inelastic effects are considered when lattice structures are subject to finite deformations. As an outlook, we are currently working with some industrial partners on industrial applications of these models. We want to include and study more the effects of uncertainties. Then we'd like to combine this also with design optimization with the methods that we have developed there, and also work on the improvement of the nonlinear elastic and the plasticity models when they apply to beams. And finally, if we think of 4D printing, then we can, of course, also enhance these inelastic models with further physical effects, so include thermal behavior or include the internal variable models that we need in order to model the shape memory effect accurately. So with this, I'd like to thank you for your attention, and I'm looking forward to any questions.